Hello ChemComm. Today is the beginning of Unit 5, where we take a look at the atom and its parts that make it up and the history of the model that we currently have of the atom. If you did the history of the atom activity with us in class, these are some of the names that should be familiar to you at this point in time. If we take a look here, we learned about how Democritus philosophically thought about the smallest building part of all matter. But we didn't get evidence of that atom until we get to Dalton in 1803 with his billiard ball model. Becquerel did research with X-rays and radioactivity. Crook discovered the charged particles within the atom. Chadwick discovered the neutron. And J.J. Thomson discovered the electron. We also get to Rutherford, who did the gold foil experiment and bombarded gold foil with alpha particles. And that showed him that there was a small dense nucleus in the center of the atoms. And finally we get to Schrödinger, who used equations to give probable locations of electrons around the nucleus, which we call electron clouds. The electron cloud model is probably the most accurate representation of the atom we currently have. Other scientists we talked about were Marie Curie, whose study of radioactivity laid the groundwork for some of the experiments done about the atom. And we talked about Niels Bohr, who came before Schrödinger and put the electrons and energy levels around the nucleus. Definitely make sure you're familiar with those scientists. They really help you understand how we got to where we got with the model of the atom. Let's go ahead and proceed with talking about those different parts. An atom is the smallest part of any element or substance that can't be broken down any farther. So if I have an atom of silver, it's the smallest part that still retains the properties of silver. There are three main parts of the atom: the proton, the neutron, and the electron. These particles are so small that we use something called an atomic mass unit to measure their mass. The atomic mass unit is based off carbon-12 atoms, and we divide carbon-12 atoms mass by 12, and that gives us roughly the mass of 1 AMU. Protons and neutrons have a mass that's pretty close to 1, and so when we add up the mass of any atom, we usually just count them as 1. You'll also notice that electrons have a very, very small mass. Because of this, when calculating the mass number of an atom, we don't even use the electron as part of that mass. So these subatomic particles are all around the atom. The neutrons and protons are located in the nucleus, and the electrons are in energy levels outside of the nucleus. Neutrons are neutral, protons are positive, and electrons are electrically negative. We've already talked about the mass of an electron. Its mass is negligible, or it's not significant enough to count into the mass of the atom. So if we take a look at this chart here, it kind of gives us an idea of the different particles that we're going to have within the atom, and it gives us their charge, their mass, and their location. Make sure you can differentiate between these three particles and their characteristics. This is just a real quick diagram. It shows us an example of a Bohr model. We can see that within the nucleus we're going to have protons and neutrons, and then on the outside of the nucleus in energy levels we have our electrons. There are different kinds of models when we get to drawing atoms. We'll go through a couple of those here in a couple slides. Before we do that, we really need to understand the periodic table and how the numbers on the periodic table help us know things about an atom. Let's start with the atomic number. The atomic number is equal to the number of protons. This is what defines an atom as itself. So we know that every hydrogen atom only have one proton. If you add a proton to that, it's no longer hydrogen. It would be the next element, which is helium. So the atomic number is what defines the element, and it's also how many protons that element has. Another number that we need to talk about that's not on the periodic table is the mass number. The mass number is specific to a specific atom of any element. And the mass number is the protons plus the neutrons of that atom. So let's suppose we look at the atom uranium-238. This 238 is telling us the mass number. We call this a nuclide. It's when you have the symbol with the mass number. And I know that the mass number is the number of protons plus the number of neutrons. If I look at the periodic table, I see that uranium is number 92 on the periodic table. That tells me that it has 92 protons. And I know that we have 238 as the mass number. So now I can find the number of neutrons using subtraction to be 146. All of these equations are just different ways to show the same math problem. you can solve for protons, you can solve for mass number, you can solve for neutrons, depending on which numbers you know and which numbers you don't know. Sometimes elements have different types of atoms, or what we'd call different isotopes. For instance, here are two different examples of lead. We have lead-210 and lead-206. Now, both of these are lead, and what that means is they both have to have 82 protons. If you look at the periodic table, you can see that the atomic number for lead is 82. Every element of lead has 82 protons. The only way that two atoms of lead can have two different masses would be if the number of neutrons is changing. Let's look at these three examples of hydrogen. Protium, deuterium, and tritium are just proper names of isotopes of hydrogen. If you look, you have one proton for each. That is what makes them hydrogen. They all have one proton. But we are changing the number of neutrons, 0, 1, 2, and therefore that would change the mass number. 1 plus 0 is 1, 1 plus 1 is 2, and 1 plus 2 is 3. So an isotope is simply just the same element, or an atom of the same element, but it has a different mass number because it has a different number of neutrons. And you can see down here, remember protons and neutrons are in the nucleus. So here's my one proton, this is protium. Here's my one proton, one neutron, this is deuterium. And here's one proton, two neutrons, this is tritium. The prefixes for those proper names are based on the number of particles in the nucleus. Protium has 1, deuterium has 2, and tritium has 3. Here's some more isotope work with mass numbers. So we know that mass equals protons plus neutrons. So carbon-12, 6 protons and 6 neutrons. Where did this 6 come from? It came from the periodic table because carbon is element number 6. This is another isotope called carbon-14. So now the mass number is 14. The number of protons is still 6 because it's carbon. And then you have 8 neutrons this time. Here's 3 different isotopes of uranium. Notice uranium is element number 92 right here. So I can fill this out all the way down. Since these are all uranium, I know that they're going to have 92 protons. So the question becomes, how do we get from 92 to 234? How many neutrons do we need? If you take 234 and subtract 92, you get 142. This uranium has a mass of 1 more than uranium-234, so this would have to be 143, and this has 3 more than that, so this would be 146. So what makes these isotopes uranium is their 92 protons. Numbers of neutrons can change, which will change the mass number. You can also notice down here at the bottom that those different isotopes have slightly different radioactive properties based on the number of neutrons. And that gets into nucleus stability, which we'll talk about in a later section. One thing that you need to be able to do is draw a Bohr model of some of these atoms. So this wants us to draw sodium-23. The first thing we're going to do is probably look at the periodic table and figure out what's the atomic number of sodium. If you look at sodium on the periodic table, you'll find that the number of protons and the atomic number is 11. So let's draw those 11 electrons in the nucleus. If you look in those protons, I put a plus symbol because protons are positive. On the right, I'm drawing a simplified version of the Bohr model of sodium, which is a little easier to draw. Now, the next thing is that we have a mass number of 23. That means my 11 protons have to be added to 12 neutrons to get to that mass number of 23. So let's draw 12 neutrons. For the time being, we're going to assume all our atoms are neutral. They are not ions. And so because of that, we're going to put 11 electrons around the nucleus. The first energy level will have 2 electrons. The second energy level can hold 8. So at this point we have 10 total electrons, which means we need 1 more in the third energy level. Notice that I put a negative sign in each of those electrons because electrons are negative. Those would be 2 drawings of the Bohr model. I prefer the one on the right. It's easier to kind of understand the different particles of the atom. So there is one more number that we haven't dealt with on the periodic table, and that's the atomic mass. That is literally the average of all the isotopes. So we talked about how there's carbon-12 and carbon-14, and there's all these different types or isotopes of uranium. So the question is, how do they get the number that's on the periodic table, which isn't a whole number, it's like an average. And that's exactly what it is. It's a weighted average of all the isotopes that we know. Let's use boron as an example. Boron has two isotopes, boron 11 and boron 10. You might think, well, the average would be 10.5. The problem is there's a lot more boron 11 in samples of boron than boron 10. And what that means is we have to do a weighted average. What we do is we take each isotope and multiply them by the percent that they represent. So we're going to take 11 times 0.8, and we're going to take the mass of 10 times 0.2. That gives us 8.8 and 2, and now what we would do is we'd add those together, which would give us 10.8. And if you look at the periodic table, the atomic mass for boron is 10.8. So it is technically an average, it's just a weighted average, and so you can't just add them together and divide by 2. One type of question that you're going to be asked during this section is to identify numbers of protons, neutrons, and electrons based on information you've been given. So let's take a look at hydrogen. First of all, it tells us the name of hydrogen, so we know we can look at the periodic table and find out a couple things. The first thing we can find out is we know that the symbol is H. We can also look and find out that the atomic number is 1, and that means I know the number of protons and the number of electrons are both 1. The mass number, I would add protons plus neutrons because mass number equals protons plus neutrons. So 1 plus 0 in this case is 1. Next one we have here is sodium, that's Na, and it's number 11 on the periodic table, which means we're going to have 11 protons and 11 electrons. Mass number is protons plus neutrons. 11 plus 12 is 23. We drew a model of that isotope. Boron, element symbol is B. The atomic number is 5. Number of protons will be 5. Number of electrons will be 5. 5 plus 5 is 10 for our mass number. Let's move on to this one down here, letter E. If you look, we've got neutrons 115 and 77 electrons. That would tell us that we have 77 protons, and then our mass number would be 77 plus 115, and that would give us 192. The atomic number would be the same as the number of protons, which is 77, and the question is, what is this element? We can look at the periodic table at number 77. It is iridium. The symbol is Ir. So you can see sometimes I can give you bits and pieces of information and require you kind of work backward to figure out what element it is. There's a lot of different ways to do these problems. I left D and F blank there for you. See if you can figure them out and check them with the notes. Good job today, guys, working through the information about the atomic model. Hopefully, after a couple days of practice with these kind of problems, you'll be able to identify all the different parts and where they're located in the atom and know, based on the periodic table, how many protons, neutrons, and electrons are in those atoms. Great job. We'll see you soon.